CBT Nuggets JNCIS Security Series Overview of High Availability Clustering. Well, this nugget should probably be called Chassis Cluster because that's exactly what we're going to do to get network node redundancy by grouping up a pair of SRX devices, the same kind of device, okay? Has to be the same platform running the same version of the Junos OS. So let's take a look at an overview of how this feature works. Okay, high availability, believe it or not, is an important part of security because your security appliances are in the line of traffic. So they represent a choke point or a point of failure. And the last thing you want in your security design or your traffic flow is a single point of failure. It also ties into your disaster recovery plan as well. So you want to have a chassis cluster of two identical devices. So two of the same platforms, both running the same version of Junos. You're going to have a control port between the two, in this case, two SRX 240s. Control ports that are going to link the control plane of these two devices. That control plane, it's a lot like what we call in Cisco a failover interface, okay? You're going to use it to sync up the configuration between the two devices. It'll also sync up or synchronize the kernel state between the two SRXs. It also provides high availability for interfaces and services between these two devices in the cluster. Then you'll have a fabric port on each SRX that connects to form a unified data plane. One of these devices, the first device will be the primary device, and the second device will be the secondary device. Once you designate the device being primary or secondary, they will always be primary or secondary. Even if the primary device fails over to the backup device or the secondary device, and the secondary device is active in an active standby scenario, that secondary device is still a secondary device. It just happens to be the active device. Keep that in mind. Now, even though these seem to be the same device, the SRX 240 with the same Junos operating system, they can have different PIMs. So, for example, they don't both have to have these ADSL 2x2 PIMs in them. Those can be different. But the nodes in the cluster will share the same configuration, and the cluster itself is identified by a cluster ID number or cluster-ID. The cluster node is identified as node 0 and node 1. So the first one, if it's this one up here, would be node 0. The second one down here would be node 1. You also have a logical construct or a container known as a redundancy group. And the redundancy group contains the node object. So this chassis cluster would be represented by a redundancy group. You'll have a primary on one device and a backup on the other device. If the redundancy group fails, okay, let's say both of these in the cluster, if the redundancy group fails, then all of the objects are going to fail over. Now, a redundancy group, as we're going to see in this next diagram, each redundancy group has one RETH, R-E-T-H, or redundant Ethernet interface. Let's take a look. Let's look at the SRX 240 in one of your most common deployments at a branch or a remote office where you have an active passive cluster where only one device is actually passing traffic at any given time. So what we have is two SRX 240s. Again, the PIMs can be different, but the Junos is the same, the model's the same. We have this trust zone. We're connecting to downstream switches. We've also got upstream switches. So in the trust zone here, we've got our redundancy group 0. Each one of these interfaces on the first one here, we've got our node 0. We have gigabit Ethernet 006. Over here on node 1, we have interface gigabit 506. These are both in redundancy group 0, and the redundant interface 0.0 represents this redundancy group. This, of course, has an IP address to it, so you have two interfaces that are basically represented by one logical redundant interface, RETH 0.0, with IP address 10.16.8.1/24. Out here, we have in the untrust zone this gigabit 005 interface on node 0, and on node 1 we have gigabit 505. These are part of redundancy group 1. And this is the redundant interface 1.0. So these two interfaces are part of this redundancy group, represented by this redundant interface 1.0, which has a IP address of 1.2.0.233/24. Now, as you can see here, we can have more than one redundancy group configured on an SRX. In this case, we have two of them. You can have up to 128 redundancy groups. So obviously for an enterprise, large enterprise deployment, or a service provider, you would have many, many more redundancy groups. Now remember that this redundancy group concept here is really an abstract kind of entity. All right? It basically manages the objects, and each redundancy group is an independent unit of failover and is primary on only a single node at a time. So for example, over here on node 0. Let's continue on talking about our SRX 240 in an active passive mode, which by the way is one of only 3 basic modes of operation. Okay, you've got active, passive, active, active, and a mixed mode. At this level in the JNCIS security, we're looking at the active passive cluster. Now, what about the routing? Okay, obviously, there's routing going on, and we have a routing engine. So let's kind of talk about that for a second. When you have an SRX cluster, each SRX is going to have one active RE, routing engine. So each one of these has an active routing engine. So when you create your cluster, you're going to have 2 routing engines working in concert to provide your redundancy. And again, this concept, this cluster, actually leverages code from the Juniper TX Matrix series. Now, the Junos operating system has a limitation where you can only support 2 routing engines per device. So, the SRX cluster can only have 1 RE per chassis. When you combine them together, that's where you get your 2 RE limit. Now, going back to this concept of the RETH, or the redundant interface, this is a Junos aggregate Ethernet interface, and it has its own kind of special MAC addressing that's assigned to it. We see here that we've got, kind of a network load balancing type IP address that gets assigned. This is what all the upstream and downstream hosts are going to see, but it uses a special MAC address, which is a combination of the cluster ID and a RETH number. With the cluster ID, keep in mind that each cluster has to have a unique identifier among all of the members of that cluster. And then, of course, we have the node ID. Node 0 and node 1, for example, are the 2 devices within that cluster. And so all of the objects and resources that would be failing over from the active to the passive device would be the redundancy group, right? Now I mentioned that, there's several modes. There's active passive, there's active active. Obviously with active active, both devices are going to be processing traffic simultaneously, which means you may have asymmetric traffic. You may have traffic that is sourced coming through one switch, coming in one direction through one SRX, and going back to the other SRX. Typically, that is a undesirable scenario, but it can happen in an active-active scenario. Let's kind of focus, though, on really the characteristics of active-passive. Now, by the way, before we get into the active-passive, which is really the main focus of this nugget, what about this line right here that connects RETH 1.0 with RETH 0.0? Well, that just happens to be our redundancy group. And it's the first one, so it would be redundancy group 1. Okay, so both of these RETHs belong to redundancy group 1. Okay, so with active passive, we have our first data plane, which would be here. This first data plane is the one that's actively passing the traffic. The second SRX data plane would be sitting by, okay, passively on standby. If there's a fault condition, then the passive data plane will take over and become the active one. Now remember, the role of primary and secondary, that doesn't change. Now, how does it accomplish this? Well, it has one data plane redundancy group, which we know is group 1, and one or more redundant Ethernet interfaces, or RETHs. So let's say RETH 1.0 goes to the internet, and RETH 0.0 goes to the internal network. Node 0 is the active node, so all the traffic is going through this SRX to and from the trust zone to the untrust zone, or the internet and the internal LAN. Over here, we're not active. This is active. We're just patiently waiting, okay? Let's get a little cloud thought there. Waiting. So these interfaces, by the way, they're physically up, but they will not be able to pass traffic until there's a failover. But because there's replication of information like synchronization of the configuration, the kernel, and other information, then it's ready to take over. And if it does, it'll have the same session information. So that's what we call a stateful failover. Let's pretend for a moment that node 1 here is the active. Pretend like this is the active one, okay? Now, normally, if this SRX were in standalone mode, okay, and you log in and you're in configuration mode, right? All of the active users who are logging into this SRX will actually be able to see the configuration and edit that configuration, right? And if you allow each user's changes to be seen by the other users on the device, let's say, I got J Conrad, I got M Shannon, I got root. If you're allowing the other users to see those configuration changes, that is referred to as a shared configuration. Now, why am I talking about this? Well, it's important because once you enable chassis clustering on these SRXs, the devices have to be configured in what is called configure private, aka private mode. Also, you can no longer, let's put the line through it, you can no longer do commit confirmed, which you've seen me do many, many times. Okay, this allows you to roll back, right, to previous configurations if you mess up. Great features, but you can't do them in clustering mode. Why? Well, stability. There's a whole bunch of information going on between these two devices at the data plane and the control plane. So you want to minimize chances for there being differences between those two devices. So no commit confirmed. Kind of makes sense. Now, obviously, we've been leading to this now, but the first thing we have to do to create a cluster is to place a device into cluster mode. So this actually involves triggering a special service or a special daemon, the JSRPD daemon. And actually what you're doing is you're just setting some special bits in NVRAM on the SRX. And by the way, you have to reboot. This is one of those situations where it's kind of a bummer. We don't like to reboot it, really ever if we don't have to, but we have to reboot. So you run a special command in the operational mode, and you have to have super user privileges. So in my case, I would have to be the root user or M Shannon, which we know are both super users. Okay, so let's kind of go take a look at some of the syntax that we would go through. And again, we're keeping this at a very high level, very basic, very fundamental for the JNCIS security series. Okay, so we're gonna look at a complete soup to nuts configuration of a chassis cluster on two SRX 210 devices. This is a very affordable solution, and it's one that hopefully you'll see what's going on here. Now, what we have to do first of all is really diagram this thing out, because as you can see, we're going to be using 5 interfaces from each device to accomplish this. Okay. Now, the most obvious interfaces I want to point out to you, and we've got 2 devices. Okay, we've got device A and we have device B, right? And of course, we're going to have device A in this active standby environment or active passive environment as our active device, and this will be our passive device, right? So the 2 most obvious interfaces are gigabit 000 on A and gigabit 000 on B. These are the devices that are going to go to the untrusted network, up to the service provider, okay? These interfaces are both a part of RETH 1, okay? 1.0, obviously. We have our unit number there. So RETH 1 represented by the IP address of 1.2.0.233/24, okay? So that's the first obvious thing. The second thing are the inside or the trusted interfaces, and I've got these right here. So these are on fast 002 on each device, right there. So fast02 on each device, those both go to the trusted zone, or, and again, remember we're still in a single redundancy group. Okay, this is all basically redundancy group 1. And we've got these interfaces going to reth0, or it would be reth0.0. Okay, and then these are represented by the IP address 10.16.8.1/24. Those are the obvious interfaces, right? And we know that the data plane traffic is going to be flowing through gig E000 and FE002 on the primary device. These interfaces over here will be activated, but they will be in passive mode, or they'll be standing by, waiting to fail over in case we have a failure on device A. Now, the other interface is pretty interesting. We're going to manage these devices, and this is really the best way to do this and to use these interfaces the way I'm showing you. So here's the management station. So we're managing both of these devices on FE006. So you'll notice that our management station, which can be connected to a switch, for example, is going to those interfaces. Now let me tell you something right off the bat here about these interfaces, and it's very important. Okay, I should have probably started this out talking to you about this. As we look at these interfaces that we're going to be using to manage the devices, and we're going to be looking at our control interfaces and our fabric interfaces, or the data plane. It's important to know that layer 2 Ethernet switching is not supported in chassis cluster mode. Okay, for these devices. So let's say if you're running these things right out of the box and you have the factory default configuration, you'll need to go through the process I showed you earlier in this Nugget series to delete the Ethernet switching configuration before you enable the chassis clustering. Okay, so I'm not going to show you that step. You already know how to do that. And you cannot, enable chassis clustering and then decide to delete the Ethernet switching settings on these interfaces after the fact. Okay, so make sure you disable Ethernet switching. Okay, we obviously have two identical models, okay, and they're running the same Junos operating system. We're going to look at FastE006. This will be the interface that we use to manage these devices. And by the way, FAST006 will actually be used as let me jot this down for you. These will actually be the FXP0 management interfaces. So we'll use these FXP0s, which will be assumed by 006 on both devices. This is how we individually manage the devices now. So you want to make sure that you don't configure FE006 on either device with an IP address, because that would override the FXPO configuration. So you want to go ahead and strip away any IP addressing you might have on this interface before you add it to your cluster. Okay? Now, we're going to connect the two devices together on the control interfaces using FE007 on both devices. And by the way, that is the default setting. So if you're using an SRX 100 or an SRX 210, they're going to, by default, when you enable clustering, they will expect these ports, 07 on both devices, to be your control port. And actually, the nomenclature will actually change. Okay, this will be FE007, and this will be changed to FE207. So after the clustering happens, there's some renaming of these interfaces. And for example, these will become FXP0. As a matter of fact, these will actually become FXP1 after the clustering. Okay, so 007 will become FXP1 on both devices. I know it's confusing, okay, but FXP1 is the control link between the two appliances, okay, and it happens to be FE007. And don't forget, by default we want to use FE006 to manage these two devices. That will become FXP0 on both devices. Also, Juniper highly recommends that for this control link here, you want to directly connect them, okay, if you can, a directly connected cable between the two. If you have to use a switch between them, you want to go up and do some research on Juniper. Now, there's another link. Okay, remember, that's only 4 of the links, right? We've got the outside, we've got the inside, we have the management, FXP0, we have the control link, which is FXP1. But what about this one right here in blue? Okay, well, that is gigabit 001. That's going to be our fabric link. So gig E001 will be the fabric link, there it is there, on both of these devices. And of course, after the fact, this will be 001, this will be 2001. So if you have to go back and rewind over that and look through it again, that's what it is. And so you want to make sure that you understand completely what's going on here, and you want to have this all diagrammed out before you configure this. Okay, so now what I'm going to do is I'm going to shrink this diagram down, and I'm going to put in below the actual syntax step by step in how we would configure these devices. Okay, this first command we have to do on both devices, and then after that we will just configure most of the commands from here on out on device A, and that will be replicated over to device B. So the first thing we do on device A is set chassis cluster, and then put in the cluster ID of 1. That has to match on both sides. So we'll issue this command on both devices. But over here, this is node 0, so it's node 0. Over here is node 1, so we do node 1 over there on the right-hand side. And when we're done, we need to reboot. Have to do that. It's the only reboot we have to do. Okay, now these commands are all going to be done on unit A over here. Okay, so we'll set groups. We want to say first on node 0 the system host name, and we're going to call it SRXA. Then we'll set groups node 0 interfaces, and we'll say for FXP0, which we know is fast 006, unit 0, its family INET, and then the address, we'll say the management address is 172.16.1.1/24. Then we're also, notice we're going to do this, we're going to set this for the other device, but on device A. So we're going to say set groups node 1 over here, system host name SRXB, and then set groups node 1 interfaces FXP0, which is right here. We'll say the address is 1.2/24. That's our management address. And then we have to do this final command here. It's kind of weird. You have these quotes with a $sign and then this variable. This is to make sure that the individual configurations for each node that we set in these commands right here are applied only to that particular node. Okay, this command is necessary because we're doing this all over here on this device. Okay, the next thing we have to do is set the fabric interfaces. That's basically exchanging the data plane information. Now you might be asking, why don't we have to configure the control plane interfaces? Remember FastE07 on both sides, which is going to be FXP1 as a matter of fact. We don't have to do that. Okay, on the lower end SRX devices it's not necessary. Okay, the chassis configuration is already assuming that we're using FE007, and it will automatically send control information over those interfaces. Right? Now, if you're using some higher end platforms like the SRX 5600, for example, then you would have to go ahead and configure additional control links or multiple control links. Here, we're setting up our fabric links. This is the data plane link. So we're going to do both of this over here on device A. We'll do set interfaces FAB0, which is for this device, and then fabric options, and then member interfaces. And remember, our fabric interface is gig E001 right here. Now, even though this device over here is technically gig E001, as part of the chassis configuration, it's actually identified now as gig E201. So when we set that one, we have to say set interfaces FAB1, because it's obviously the fabric for node 1, fabric options, member interfaces, and make sure we do gig E201. That's how it's identified now as part of the cluster configuration. Okay, next we're going to set up 2 redundancy groups. Okay, redundancy group 0 is actually going to be for the routing engine. for the routing engine to fail over from the primary to the secondary. Redundancy group 1 is basically what the interfaces are going to be part of, right? Okay, so they're in redundancy group 1. So obviously, since node 0 is going to be the primary device, we're going to give it the highest priority. So the first command is to set the chassis cluster redundancy group 0, in other words, the routing engine, on node 0 with a priority of 100. So we're going to be using this routing engine. Then we'll set the chassis cluster redundancy group 0 for node 1, which is over here. We'll give that a priority of 1, the lowest priority. So we're going to be using this as our routing engine. Then redundancy group 1 is for our interfaces. So we'll say set chassis cluster redundancy group 1, and then of course node 0 is our primary device, so we'll give it a priority of 100, and of course we'll put node 1 over here with a priority of 1. Again, redundancy group 0 is for the routing engine redundancy. Redundancy group 1 are what our RETHs are members of. Okay, next we need to configure interface monitoring, right? We need to monitor the health of our interfaces that are members of these redundant Ethernet interfaces so that we can know if we have to trigger a failover from device A to device B. Now we configure this interface monitoring only on redundancy group 1, not on redundancy group 0 or on the routing engine. It's not recommended. So what we're doing first off is we're doing set chassis cluster redundancy group 1, and then we're going to do interface monitoring on gig E000, okay, and we're going to give it the highest weight. That's this interface right here. Then we'll set chassis cluster redundancy group 1, interface monitoring on FE02. That's this interface right here. Here's where our pointer, right? This, of course, goes down into RETH 0. Then we'll set the chassis cluster redundancy group 1 for interface monitoring on gig E200. That's this interface right here. Remember, it will assume the gig E200 once we configure this cluster. And then, of course, the other interface, you can see it's kind of coming down at an angle here. This was interface fast 002, but now it's interface monitoring fast 202. Make sure you give it all the highest weight. Okay, so we have to set that up to do interface monitoring so that we can know if we have to fail over. Okay, now we have to set up the redundant Ethernet interfaces, or our RETH interface, and then assign those RETHs to a zone. Let's start on the bottom here. Okay, let's just do the bottom RETH 0 first. First thing we have to do is we have to set the maximum number of redundant interfaces. So we use the command set chassis cluster RETH count 2. We've only got 2 RETHs, 0 and 1. Then we're going to set interfaces, and we'll do fast 002, right? That's this interface right here going into RETH 0. We'll say fast ether options. The parent, or the redundant parent, is RETH 0 right there. Then for 202, which we know is this interface coming down here at an angle, right? 202. We know this will be changed to 202. So 202 fast ether options, its redundant parent is RETH 0. Okay, no problem. Then we're going to say RETH 0, your redundant ether options is to be in redundancy group 1. And then finally we'll assign this logical IP address to it with set interfaces RETH 0, unit 0 family INET, and then address, as we can see here, 10.16.8.1/24. Okay, so now we've set up RETH 0 and we've placed these interfaces into that RETH and assigned the IP address. Okay, let's go ahead and do the top up here now. Okay, let's go ahead and move this up a little bit so we can see RETH 1 up here. We're setting interfaces gig E000, that's this interface right here. Fast ether options, its redundant parent is RETH 1. Okay, then interface, and we know this will be changed to 200. So set interfaces gig E200, fast ether options, its redundant parent is RETH 1. You see that right here. Then Set interfaces reth1, redundant ether options, it's in redundancy group 1. Remember, both reths are in redundancy group 1. Redundancy group 0 are the router engines within the appliances. And then finally, set interfaces reth1, unit 0 family INET with the IP address of 1.2.0.233/24, as we can see right here. Now, we still have a few more commands to finish up here. Take a look. Finally, in configuration mode, we'll set security zones security zone trust, which is, of course, down here. Interfaces reth 0.0, and then set security zones security zone untrust up here. Interfaces reth 1.0, commit, and then all of the changes will be transferred from device A over to the secondary device, device B. And that's our configuration for active standby or active passive on a redundant SRX 210 devices. All right, in this nugget of the JNCIS security series, we got an overview of high availability clustering, specifically on two SRX 210 devices. I hope this CBT nugget was informative for you. I want to thank you for viewing.